Okay. Our counting problems go along pretty well in section 8.6, but we're really thrown into the fire on part B of number 17. So here's our problem. We have a radio stations are typically identified by 4 call letters. Radio stations east of the Mississippi River have call letters that begin with W, while those to the west have call letters that begin with K. Find the number of different sets of radio station call letters that are possible in the United States. So we have 4 letters, if we stick to this convention as prescribed above. And in the first letter, we can be east, we can be west, but we have 2 options for our first choice. And then we just continue making choices, much like if we were going to the closet and choosing shirts and pants and shoes and belts. In this case, this is like a closet problem. So we have 2 choices for the first, and then after that, we're free to choose whatever letter we'd like. There's no mention that letters can't repeat. There's no mention we can't use K and W again. So then I have times 26 times 26 times 26 possible solutions at this point. And this, of course, then we all would grab our calculator here, I believe. We have 2 times 26 to the third. In this case, pretty big number, 35,152. So that would be the number of possible radio stations under the prescriptions of those types of call letters that we could have in the United States. Not too bad, just kind of your run-of-the-mill closet problem. We make a choice, and we make a choice, and we make a choice, and there's an and, we make a choice. And if the choices are independent of one another, then we can multiply, in this case, 35,152. But B is another deal. Find the number of different sets of radio station call letters that are possible if the call letters must include a Q. Well, what we know for certain is they're not going to include a Q in the first letter. And we might think along this lines. We might think, okay, how about then if we force a Q in there somewhere and we say, I'm going to make the second number be a Q. But then we may think, well, perhaps I want to make the third number be a Q. And these numbers can be whatever they want. There is an inherent danger in this thinking. What if I want to make the fourth number be a Q? And then we could say we win, or we have one with at least a Q in it, if we get this or this or this occurrences. And if we can win the first way or the second or the third or, excuse me, first, second, or third, we may be tempted to add those. The problem with this is, let's consider this number, or this call letter, K, Q, T, Q. That, I will claim, has been counted right here, but has also been counted there, and we have a double counting situation. So that may not be our best approach. Now, if we consider we win if there's a Q in there, we may be able to kind of sneak in the back door on this one and say, okay, if we win by having a Q represented in the call letters, how could we lose? Well, we'd lose if there were no Q's. So how many ways can we lose? Well, we don't have any choice for the first letters. Now we have to guarantee that we don't have any Q's. Well, we would not have Q's here if we just selected from 25 letters. And we would not have a Q here if we just selected from the other 25 and the other 25. That would be our number of choices that contain no Q. And that, of course, that would be a calculator problem as well. And we go 25 to the third times 2, and we end up with 31 to 50 of these numbers contain no Q's. Therefore, the number with Q's should be the difference? And we will pass that on to a good 6th grade math student and let them figure that one out for us.